All right, hello everybody. This video is going over the 7th lesson of Unit 3, which is on solutions and mixtures. Today you'll learn the difference between homogeneous and heterogeneous mixtures, how intermolecular forces affect solubility, and why solution composition is so important. We'll also practice calculating solution concentration using molarity, which is one of the most common ways chemists describe solutions in the lab, which is also perfect for review and exam prep. So in Unit 1, we talked about the different states of matter that you can put next to a compound in a chemical reaction, S, L, G, and AQ. Those stand for solid, liquid, gas, and aqueous. Now remember, aqueous means dissolved in water, and that would be considered a solution, which is what we're going over today. And remember from a previous unit, we talked about homogeneous and heterogeneous mixtures. A solution would be a homogeneous mixture because it is an even distribution throughout. A solution is made up of two parts, a solvent and a solute. The solvent is a substance that is doing the dissolving, so it's the greater portion of the solution. Normally when we're talking about a solution, the solvent is water. A solute is the substance that is being dissolved. Now, solutions, we already talked about in the last slide, are homogeneous mixtures. That's going to mean that the solute particles are evenly distributed throughout the solvent. So let's talk about putting salt in water when we're boiling pasta. So when you put salt in boiling water, the water is the solvent and the salt is going to be your solute. Once dissolved, the salt is spread out evenly, so the pasta is going to cook at a higher temperature in that salty solution. So it changes the composition of the solvent, and now that pasta is boiling at a higher temperature because of the salt. So in pure water, boiling happens when water vapor pressure equals atmospheric pressure. Now when we dissolve salt into water, it's going to dissociate into its Na plus and Cl minus ions, which is going to increase the total number of solute particles. And those solute particles are going to interfere with the ability of water molecules to escape into the gaseous phase, which is your vapor pressure. So fewer water molecules reach the surface with enough energy to evaporate, so the liquid or the water has to be heated at a higher temperature, which is usually why people add salt into water to boil pasta, because now their pasta is going to cook faster. The process where solvent molecules surround and interact with solute particles is called solvation. This happens because the solvent and the solute are attracted to each other through intermolecular forces called ion dipole. When the solvent is water, this process is known as hydration. So when we take NaCl and dissolve it into water, the sodium cations are surrounded by water molecules with their oxygen atoms facing inward, and that's because oxygen is more electronegative, and because it's the negative end of the dipole, it's going to be attracted to that positive sodium ion. Now, if we were to do the same exact particle diagram but with a chlorine anion, then the water molecules would be flipped so that the hydrogens, or the positive end of the dipole, would be attracted to the negative chlorine ions. And these interactions between ions and water molecules are going to keep the solute particles separated and evenly distributed throughout the solvent, which is why this is known as a homogeneous mixture or homogeneous mixture. Concentration measures how much solute is dissolved in a given amount of solution. And the most common way that we express that in AP chemistry is with molarity, or a capital M. And when we're solving for molarity, you're going to have moles of solute, which is what you are dissolving, in the numerator, and liters of solution, which is the entire volume, in the denominator. And that will give you concentration. And just so you are aware, I'm sure you learned about molality in pre-IB chemistry or percent by mass. Those are not assessed on the AP chemistry exam, so you do not have to do those on the final exam. So let's do a practice with concentration. If 6.73 grams of sodium carbonate is dissolved in enough water to make 250 milliliters of solution, what is the molarity of the sodium carbonate? So we know concentration is going to be moles of solute over liters of solution. Now we already have our volume, it is in milliliters, so in order to convert that to liters, we know in 1 liter we have 1,000 milliliters. So we would convert 250 milliliters by dividing by 1,000, and that will get rid of our milliliters. Or you can know to just move that decimal point 3 times to the left. So our liters of solution would be 0.250 liters. Now we need to get the moles of our solute. Now we know we have 6.73 grams of our solute, and we need to convert that to moles by dividing by the molar mass. So in 1 mole of our compound, we have the molar mass of that compound. In order to get the molar mass of sodium carbonate, we need to add up all of our values from the periodic table. So molar mass, we have 2 times 22.99 plus carbon, which is 12.01, plus 3 oxygens, which is 16 each. And that gives us a molar mass of 105.99 grams per mole. So that's going to go in our denominator. And now we can, in our calculator, put 6.73 divided by 105.99. That's going to give us 0.0635 moles, which is going in our numerator of our original molarity equation. So 0.0635 moles. And now we have moles over liters. So we can go ahead and put that in our calculator. And our final answer, since this is 3 significant figures and this is 3 significant figures, our final answer to 3 significant figures would be 0.254 and capital M for molarity. What is the mass in grams of solute in 250 milliliters of 0.0125 molar solution of potassium permanganate? So we know our concentration equation is molarity equals moles over liters. Now we're specifically trying to solve for the mass of solute. And I know if I solve for the moles of solute, I can convert that into mass by multiplying by the molar mass. So we're going to solve for moles, which means our new equation is concentration times volume in liters. So our concentration is 0.0125, and our volume in liters would be 0.250 liters. That is going to give us 0.003125 moles. Now that we have that information, we can go ahead and convert moles to grams in order to get the mass, which is what it's asking for. And when we multiply our moles by our molar mass, we get 0.4939 grams. And since this is in 3 sig figs, this is also in 3 sig figs, we need to have our final answer in 3 sig figs, which would change this to 494. And we are looking at KMNO4. So that would be our final answer. Once a solute is fully separated and distributed among the solvent particles, we can treat it as evenly dispersed throughout the solution. And that's because by breaking down the solute and spreading it uniformly, every liter of solution contains the same concentration of solute particles. So when we're actually forming a solution, there are 3 main energy steps that occur. The first part is actually expanding the solute, or whatever you're dissolving. So if we're talking about an ionic compound, we have to break those ionic bonds in order for that solute to dissolve. And because we are breaking bonds, that's going to be an endothermic process where we have to put energy in. The next step is expanding the solvent, or usually water when we're talking about dissolving ionic compounds. And in order to expand the solvent, we have to break intermolecular forces between those molecules to make room for the solute. And because we have to break intermolecular forces, again, we have to put energy in, which is an endothermic process. And lastly, we have our solute-solvent interactions. And because bonds or forces are being formed between the solute and the solvent, it is going to release energy. So this third step is going to be exothermic. Now, what's important about these three steps is if step 3 releases as much or more energy than steps 1 and 2 consume, the overall process has a net energy release, which means it's going to be thermodynamically favorable, or it's just going to happen spontaneously. If step 3 does not release enough energy, then it's going to cost too much energy, and that solute is not going to dissolve. So when we are working with solutions, sometimes you have a solution that is way too concentrated and you need to dilute it down into a lower concentration. In order to do that, we're using the dilution equation, which is something you have to memorize. And it is M1V1 equals M2V2. So we have our initial concentration in our initial volume, and that's going to equal our final concentration in our final volume. So if we have an example like the one on the bottom here, calculate the volume of 0.1 molar copper 2 sulfate needed to make 50 milliliters of 0.05 molar copper 2 sulfate. So we have an initial concentration, and then we have a final volume and a final concentration. So we are solving for initial volume here. So that's going to be V1 equals M2 V2 over M1. So our final concentration is 0.05 molar. Our final volume is 50 milliliters, and our initial concentration is 0.1 molar. So when we do that in our calculator, we end up giving 25 milliliters. And since it did not specify, you can keep it in milliliters or you can convert it to liters, which is usually AP chemistry's preference. And that would be dividing it by 1,000. So we'd have 0.025 liters of copper 2 sulfate. All right, let's do another one of those. If 200 milliliters of 0.6 molar magnesium chloride is added to 400 milliliters of distilled water, what is the concentration of Mg2 plus ions in the resulting solution? Assume volumes are additive. So we have an initial concentration and volume, and we have a final volume. So let's go ahead and assume first we're going to solve for final concentration of our magnesium chloride. So we have an initial concentration of 0.6 molar. We have an initial volume of 200 milliliters, and we have a final volume of 400 milliliters. Now you see these milliliters cancel right out, so don't worry about converting them. And then we're going to be left with concentration, and now we do 0.6 times 200 divided by 400. And that's going to give us 0.3 molar solution, and that's of MgCl2. And because it's asking for the concentration of Mg2 plus ions, in 1 mole of MgCl2, I only have 1 mole of Mg2 plus ions, which means our concentration would be the same. So 0.3 molar Mg2 plus. And then our last example for today, a 40 milliliter sample of 0.25 molar potassium hydroxide is added to 60 milliliters of 0.15 molar barium hydroxide. What is the molar concentration of hydroxide ions in the resulting solution? So in order for us to get concentration of OH minus ions, I need moles of OH minus ions over the entire volume. So we already know the entire volume because we have 40 milliliters and 60 milliliters, so that'd be 100 milliliters total. and 100 milliliters is equal to 0.1 liters. So we already have the volume, but we need to get the moles of hydroxide ions. And the way we're going to do that is solve for hydroxide ions in both of these concentrations and add them up. So for our moles of KOH, we just take our concentration and multiply it by our volume, and we get 0.01 moles of KOH. And since there's only one hydroxide in KOH, that means we have a 1-to-1 ratio. So 0.01 moles of OH minus. Now we're going to do the same thing for barium hydroxide. We take the concentration and multiply by its volume, and we get 0.009 moles of barium hydroxide. Well, in barium hydroxide, we have 2 moles of hydroxide ions, so we need to multiply that by 2. So now we have our moles of hydroxide. We can add those together, and that will be the numerator of our concentration. So we have 0.01 plus 0.018 gives us 0.028 moles of hydroxide ions. So 0.028 divided by 0.1 is going to be 0.28 molar for our hydroxide ions. All right, I hope that video helped. If you have any questions, please let me know. I'm always happy to help. Have a great day. Bye.